Ladies and gentlemen, class recording has started. So, plan for today is we want to get into this idea of average atomic mass and ultimately tell you about that other number that shows up on the periodic table. But first, before we do that, we've got to go over a couple of terms. Isotope. We discussed isotopes last Monday and then last Tuesday. What are isotopes? If we say two atoms are isotopes, what would that say about them? Maddie, go ahead.
Elements that have the same number of protons but different number of neutrons.
Same protons, different neutrons. And that means that that would have the same what, but a different what. If we talk about description of those atoms. Very good.
They're like the same element on the periodic table, but they have a different atomic mass.
You're getting closer. Atomic mass is definitely not the word I want you to use right now. They have a different mass number, but they have the same atomic number. Alright? So, elements, atoms that have the same number of protons, different number of neutrons, and that means that they have the same atomic number, but different mass numbers. Isotopes, same protons, different neutrons, same element, different mass. That means they have the same atomic number, but different mass numbers. Alright, so, you threw out that other word that I didn't want you to throw out right now, right? Which was what? Atomic mass. So, let's talk about that. Because those two things are different. Mass number and atomic mass are not the same thing. What does the mass number tell us? What was our definition of mass number? Okay. You want to
The number of protons and neutrons in the nucleus.
Number of protons and neutrons in the nucleus. Meaning that mass number is always going to be a whole number. It's a counting thing. You're counting the number of protons, and you're counting the number of neutrons. Mass number is always a whole number. It's a counting thing. But if you look at the periodic table, right, each square has a couple of numbers. One of those numbers is the atomic number. The other one, most of those squares, the other number that's in there is not a whole number. So is that number the mass number? It's not. Okay? That number is the average atomic mass. So we'll tell you where that comes from right now. Okay? First, average atomic mass is a relative scale. It's not a measurement per se, it is a comparison. For example, does anybody have their bean lab from yesterday out right now? Does anybody have it like in their hand? If somebody doesn't have it out, well, Katie, do you have it out? All right, Katie. Will you do something for me, Katie? Look at the row that says relative mass factor. Yes? Okay. What was your smallest bean?
The black-eyed pea.
Okay, black-eyed pea. And in the row that says relative mass factor, you should see that black-eyed pea has a number 1, yes? Okay. All of you, if you're looking at your data, if you're not, you should see similar numbers here, okay? So, Katie, look under kidney bean. Underneath kidney bean in the relative mass factor, do you have a number that's close to 2?
Yeah.
Okay. So Katie said that in the relative mass factor, her kidney bean number is close to 2. Okay. What does that mean? That the relative mass factor for kidney beans is 2? Nicole, go ahead.
Yeah, I'm almost afraid to answer, but is it like 2 times the size of the black-eyed pea bean?
Yeah, it's telling you that it's 2 times the size of the black-eyed pea. Katie, underneath lima bean, do you have something that's close to 5? Okay? What is that saying? If lima bean's relative mass factor is 5,
Oh, I got this.
go ahead.
The lima bean is 5 times the size of the black-eyed pea.
Okay. That is a relative scale. What are we doing with those numbers? What are those numbers doing for us, Mike?
It's comparing the smallest bean to the size of the other beans.
It's comparing the size of the other beans to the smallest bean, but it's basically comparing the size of the beans. But before we can do that, before we can set up that scale, what do we have to do? Before you can set up a scale to compare things to each other, what do you have to do first? Far ahead.
Put them in the same unit.
Put them in the same unit. I'm kind of getting there. Katie, what are you going to say?
You have to multiply the mass of everyone by the smallest.
Now that's the next step. Before we set this up. Before we set up a comparison, what do we have to do?
The thing that you're going to compare it with.
We have to set up the thing we're going to compare it with. We have to set up the standard that we're going to compare all the other things to. That's what we have to do with atomic mass as well. The standard that we compare all other atoms to is the carbon-12 isotope. Carbon-12 is the standard to which we compare all the other atoms. We talk about them relatively speaking in terms of that atom. Now, what was our basis for comparison for our lab yesterday? Katie, what did we compare all the other beans to?
0.218.
In the relative mass factor, what did we compare all the other beans to?
1.
Which was what bean?
The black-eyed.
The black-eyed pea. We compared all of them to the smallest one, and we called that 1. Okay? The one thing that makes this scale a little different is that we're not calling our standard 1. We're calling it 12. Exactly 12. Okay? The carbon-12 atom we call exactly 12, and then we compare all the other atoms to that. Good so far? Okay, let's see how this all works. Right underneath that, right underneath this on your outline, you have these two tables. I'm going to grab the first one here. So, I'm going to make this a little bit smaller. And then before we talk about this table, I'm going to ask you to do me a couple things. First, I want you to cross off this column, just in the top table. I want you to cross off this column, just in the top table. And then I want you to cross off this column, just in the top table. Good so far? Okay. There are two atoms that this table is comparing. Carbon-12 and carbon-13. Remember from earlier in the week we had that other notation, that's the mass number that shows up on top. Based on the fact that this is carbon-12 and this is carbon-13, you should be able to tell me how many protons, how many neutrons, and how many electrons each of those two atoms has. In the space just to the left, right over here, write for me how many protons, how many neutrons, how many electrons those two atoms have. Go. Carbon atoms should tell you what about them? Katie, go ahead. Either one of you, I don't care.
That they all have 6 protons.
They both have 6 protons. And that means that they also both have what?
6 electrons.
6 electrons as well. That being the mass number, though, you should now be able to tell me how many neutrons each of those has, Maddie.
6 and 7.
And 7. Good there? Alright, now let's talk about this atomic mass column. We said that for atomic mass, we assigned the carbon-12 isotope this value of 12. Exactly 12. Where does most of the mass of an atom come from? Nucleus, and so what's in the nucleus, Matt?
The neutrons and protons.
Neutrons and protons. So what did we do going from carbon-12 to carbon-13? We added what?
Neutrons.
Added one neutron. We went up by one neutron. What does our atomic mass go up? By about what? About 1. So we're saying that the carbon-13 atom is about 1/12 bigger than the carbon-12 atom. Does that make sense? Okay. Good so far? All right. Next table. Next table. So, get rid of this, but keep that column. Magnesium 24, magnesium 25, and magnesium 26 are 3 isotopes of magnesium. Using your periodic table, once again, how many protons, how many neutrons, how many electrons do each of those 3 atoms have? Go. Find magnesium on your periodic table. It's over on the far left if you're having a tough time finding it. How many protons, how many neutrons, how many electrons do each of those 3 atoms have? The fact that they're all magnesium should tell you something, right? Emily? They all have 12 protons, and they all have 12 electrons. And that makes the difference the number of neutrons, right? Emily, how many neutrons does magnesium 24 have?
12.
This has 12 neutrons, this one has 13, and this one has 14. Okay? Alright. If you look at magnesium 24 and what makes it up, and when you look at what makes up carbon-12, how big is magnesium 24 compared to carbon-12? 2 times as big, right? Has 12 protons, 12 neutrons, 12 electrons, where carbon-12 had 6 protons, 6 neutrons, and 6 electrons. Yes? So if we look at its atomic mass, what do we see about its atomic mass? Is magnesium 24 twice as big as carbon-12? Is it twice as big? Not quite. If it was twice as big as carbon-12, what would its atomic mass be?
24.
Be exactly 24. But it's not exactly 24. Why not? It's just not. We measure it that way. What does that suggest to you, maybe about the things that make up atoms? If we doubled the number of protons, neutrons, and electrons, but haven't exactly doubled the mass, what does that sort of suggest, Elise?
Not all atoms have the exact same mass.
Not all, how about instead of not all atoms have the exact same mass, how about not all nuclei or protons, neutrons, and electrons necessarily aren't exactly the same? Because if they were, and we doubled the number of them, what should we see about the mass? Be exactly double, but it's not. Okay? How do we know? Just not. That's how we measure it. Okay? But if we then go from magnesium 24 to magnesium 25, right, we see it goes up by how much? About? By about 1. And then if we go to magnesium 26, it goes up by about 1 more. Okay? However, take a look back at your square on magnesium. Take a look at the magnesium square on your periodic table. Its atomic number is 12, and then there's one other number in there, right? What is that other number? What is the actual number? Okay, Farah, go ahead.
24.39.
The actual number is 24.31. Is that this? Is that this? Is that this? No. So that number of 24.31 doesn't give you the atomic mass of any of these 3. So what does it give you? The average atomic mass. But about 24, and this is about 25, and this is about 26, the average of those three numbers is 25. That's not 25, it's 24.3. Why? Oh, good.
Because these numbers are in fact.
Okay. If we look, it's not because of that. It's not because of these numbers. It's because of these numbers. Okay? What is the title of that column? Natural abundance. If we get a sample of magnesium atoms, okay? Let's say a random sample of 100 of them, which you really can't do because they're too small, but let's say we got 100 magnesium atoms. 79 out of those 100 magnesium atoms would be magnesium 24. 10 of those 100 atoms would be magnesium 25, and 11 of them would be magnesium 26. Does that make sense? That's what we find naturally. There are 3 isotopes of magnesium. Most of the magnesium atoms out there are magnesium 24. It has the highest percentage. But 10% of them are magnesium 25, and 11% of them are magnesium 26. So when we take the average, can we weight the 3 of them equally? Just like if you have in a class, right, if you have 3 5-point quizzes, and you get 100% on all the 5-point quizzes, but then you have a 100-point test, and you get a 50% on the 100-point test, is your average for the class 75%? That's in the middle of 50 and 100, right? But do all those assignments count for the same weight to your grade? They don't. And that's the same thing with this as well. The average atomic mass takes into account the atomic mass of each of the isotopes, but then also how often do they show up. Good there? Yeah. So, let's fill out a little bit more here. Average atomic mass. Not all isotopes occur naturally in the same proportion. Some isotopes occur more often than others. The average atomic mass takes into account that distribution, but then also what the atomic mass of each individual element is, or each individual isotope is. So it takes into account the fact that, yeah, there might be more than one or more of one isotope versus another isotope. The average atomic mass takes into account the atomic mass of each isotope and the percentage of which they show up. I know the wording isn't exactly the same in your outline. I apologize for that. But if you're going to calculate the average atomic mass, you need to know what the atomic mass of each element or each isotope is, and then how often do each of them show up. Good there? Alright, if you flip it over on the back, you'll see these pictures. First, let me put a big box over this in the middle so we don't get confused. Okay. Over on the left-hand side over here, there is a sample of bromine. Bromine is a liquid when it's out there in the real world by itself. Okay. And we take a random sample of 8 bromine atoms. We find out there's a bromine 79, bromine 79, 79, 79, 79, and then 81, 81, 81, 81. If you average those, what's the average going to be of those 8 atoms?
80.
It's going to be 80, right? Becca, is it going to be 80 because 80 is the middle of 79 and 81?
No, not necessarily, because it depends how many of each atom you have.
Right. not necessarily was the best answer, right? Yeah, 80 is between 81 and 79, but more importantly, how many of each are there? 4 or 4, right? But if you go here, right, 35, 35, 35, 35, and 35. 6 35s, but only 2 37s. So if you add up all 8 of these and then divide by 8, you're going to get a number that's closer to what? 35, because there's more 35s. Does that make sense? Yeah. So, how do we account for that when we're calculating the average atomic mass of an atom? This formula takes that into account. For each individual isotope, you need to know its atomic mass, and then you need to know how often does it show up in nature, or what percentage of the atoms out there in nature are that isotope. So you put the mass in over on the left-hand side, you multiply it by a fraction. You're basically in here turning percentages into decimals. That's all that middle step does, right? If you take a percentage and divide it by 100, it turns it into a decimal, yeah? Is that good math class-wise, right? That's all you're doing there. And then you get a contribution. If you add up all of the contributions of all of the different isotopes, you end up with the average atomic mass. So let's say I'm going to give you some of these problems for homework, and you want to check and see if you're right. How do you know if you get the right answer when it's all said and done? Barb?
Just check the atomic mass on the periodic table.
Don't check the atomic mass on the periodic table, check the average atomic mass on the periodic table, right? That should give you the number on the periodic table. For example, okay, here's some data for chlorine. So, how many isotopes of chlorine do you see here in this table? 2, so you only have to do 2 calculations. So you start off with chlorine 35. So you take this number for chlorine 35, 34.96885. I'm going to give that number to you. That's a known value that I give to you. Okay? Then, you multiply it by a fraction. What goes on the bottom of that fraction?
100.
100 always goes on the bottom of that fraction. And then the percentage that goes up on the top. Okay? But you have to do that for each isotope. So, 36.97790 times 24.47 over 100. Joe, you got your calculator out?
Me?
Yeah, are you doing this, or?
Yeah.
Okay. You got any answers yet, or no?
26.4119741.
We'll call it 26.411. How's that?
Alright.
Okay, did you do the second one yet, or no?
No.
Okay. Anybody got the second one done yet? Yeah, you go ahead.
9.0484921
So then, what did we say we had to do with these two numbers? Add them together. And if you add them together, I bet you'll get 34.45. How do I know you'll get 34.45? If you look at the periodic table, find chlorine. It's over on the right-hand side. At least what does it say for chlorine on your periodic table?
35.45.
There it is. We have rounding things going on and stuff like that, but you know, so your numbers might not match exactly, but they should be pretty close. Good there?
Yeah, we did that on test and it was like relatively close with the decimal.
Yeah. That's it. Yeah, Becca, that's just a rounding thing. So, all right. For this weekend, first, at the bottom of your outline, there's another set of data for zinc. But you see how many isotopes does zinc have? 5. So you got to do that calculation 5 times. Okay. Then on the back of, like I said, on the back of the problem set, where you figured out the protons, neutrons, and electrons, you have this problem set. Stand by. You have this problem set, this average atomic mass. Okay. Calculate there as well. If you look on the calendar, on September 28th, you'll see that answers are posted right there, so you can check those out. Okay? Yes, Katie, go ahead.
On the average atomic mass note sheet,
Yep.
do you want us to show our work for the thing?
I mean, honestly, I really don't care at that point. I mean, that's more for practice for you. If you know how to do it, that's fine. So, but yeah, I mean, maybe because it's the first one you're going to do on your own, you might want to show you, like, do what I did on the board there. Okay. Hey, good job, everybody, with the recording. We got done, and
Did you stop it?
not yet.
When you stop it?
I wanted to publicly praise you first.
Oh,
Then I'll stop it. So.
And we get back.
Consider yourself publicly praised.